Let's check. Is that horse dead enough? Nope. We got to keep going. So we're going to keep beating that dead horse, and we're going to be continuing to talk about geometries, but now we're going to relate them to what we learned a little bit about covalent Lewis structures and kind of bring the two together, hopefully. At least that's the ideal here. So first thing we're going to do is let's just pick out I guess maybe one of the ones that we ended with. In a previous video, we saw something that looks like this, which is formaldehyde, which is the thing they used to, submerge floating brains in and stuff like that. If you go into any biology lab and you look around and you think, gross! Most of the stuff you're looking at is in a formaldehyde solution. So that's formaldehyde. And notice I gave you a covalent Lewis structure, a couple of things to pick out, double bond, single bond, single bond. And so this carbon is going to be the site of the geometry. And let me show you how you're going to determine what geometry you actually have. Well, the first thing you always have to do is you have to count up what's called electron clouds. You'll see that resource guide on geometries is all based on that very far left side, figuring out how many clouds you have. So this obviously counts as a cloud of electrons. This counts as a cloud of electrons. And it turns out that double bond counts as one cloud of electrons, right? They're all kind of doing the same thing. So what we have is something with 3 electron clouds. And what you can do is you can say, well, then I know that I've got an electron pair geometry that involves 3 electron clouds, and that is called a trigonal planar molecule. And so you look at that thing and you say, okay, well, that's the electron pair geometry. Do I have any lone pairs around carbon? And in this case, you don't. You've got lone pairs around oxygen, but that's on the end of the molecule, right? So right here, there are no lone pairs of electrons. So in a case like that, your electron pair geometry will always match with your molecular geometry. So it turns out we also have a molecular geometry. Which is trigonal planar, right? Trigonal planar all the way around. If you have any questions about what the bond angles are, it's actually pretty easy to figure out, because if you have 3 different people that hate each other and you stake them in the ground, assuming they don't eat each other, but I've been watching a lot of zombie movies. I don't know if that really happens anymore. This coronavirus thing is totally throwing me off. So anyway, assuming that these people don't eat each other, they're going to try to stay the hell away from each other, right? And so the way that I can do that is by kind of associating myself with this 120-degree bond angle here. That is not 120. That is 120. Right? And then each one of these is also going to be 120. It turns out that if you were to search on the Googles or to research electron pair geometries, it turns out double bonds kind of force these guys a little bit more, so it might be 119 degrees. Who gives a crap, right? As long as it's somewhere near 120 degrees, all is good. How about the geometry of this guy, right? Well, once again, we're going to count electron clouds. Every single bond counts as one electron cloud. Now we've got a triple bond that counts as another electron cloud. Nothing else is around that carbon. Therefore, our life is pretty easy. It turns out that my electron pair geometry, I'm just going to abbreviate it as EPG because that's what the cool people do. This is linear. And because there's no lone pairs, we also have a molecular geometry, MG, which is going to be linear. So hopefully, at least for the really simple ones, you're starting to kind of understand the way that those various animations fit a little bit better with the Lewis structures. But let's keep on beating the horse. Let's say I'm giving a Lewis structure that looks all kinds of cockamamie like this thing. And let's redraw this into kind of a more realistic form. And what we're going to do, once again, is we're going to count electron pairs around the central atom. I'm sorry, electron clouds around the central atom. And so we saw before that double bonds count as an electron cloud. Single bonds count as an electron cloud. And it turns out here is an example of where we have a lone pair of electrons. So that lone pair of electrons is going to affect this geometry. And we have to figure out which electron pair geometry we have. Well, it's the one that involves 3. We've seen that a couple of times already. So we're going to call this thing an EPG of trigonal planar. And so the second that you choose that as your electron pair geometry, that means that everything has to have 120-degree bond angles. So let's redraw this thing, right? A lot of times people trick themselves into thinking something's linear if the Lewis structure is written linear. Well, turns out this one is definitely not linear. By the way, this is ozone, that thing you smell when there's like a lightning storm and things like that. Right? So there's a little bit more of a realistic representation of that trigonal planar electron pair geometry. Now, because we have a lone pair there, right? Like when you see a lone pair, you should go, I got to be careful here. Because what happens is that the electron pair geometry is what it's, the molecular geometry is based on this geometry, but it's a new name now that it's got a lone pair because we don't see this. We just see the bend here, right? And so the molecular geometry of this thing is going to be bent. And some textbooks call that angular, but that's how you do it. So let's try out something that has the tetrahedral geometry, because it turns out when we redraw tetrahedral geometries, we have to use a couple of new conventions. So here's another Lewis structure for a covalent compound. This is methane's Lewis structure. And so what we're going to do first of all is we're going to do the same thing that we usually do when we have to assign geometries. We count all the electron clouds. We've got 4. So you'll remember, or if you're looking at your sheet, you'll notice that we have what's called a tetrahedral geometry. And of course, since there's no lone pairs of electrons, this is also a tetrahedral geometry. But there's a little bit of a problem when you redraw this thing. It's tough to draw something that looks flat, right, on, and actually preserve its three-dimensionality, right? And so it turns out this is a convention that you'll see in a lot of movies where they're trying to make somebody seem smart. Turns out that now you're going to know all about it, so you're going to be smart too. This guy right here is the way that methane looks, right? There is an actual tetrahedral geometry. So what we're going to do is I'm going to hold this sucker kind of like this, right? And you'll notice that there's a hydrogen kind of poking you in the eyeball. Boink. Yeah, that was fun. This guy right here is poking me in the eyeball. Don't you even think about it. And what we're going to do is we're going to keep this hydrogen, carbon, hydrogen in the plane of the board. So watch what happens here. So what we do is we keep that hydrogen, carbon, hydrogen in the plane of the board. And there you can see that 109.5 degree bond angle. Now the one that just poked you in the eye, we're going to make that a piece of pie. It's not just a bond, it's a solid pie wedge right here. Pie. And then the other one, we're going to do kind of a dashed pie. That doesn't look anything like a pie. Now it's a pie. And that's the way that we're going to be able to show three-dimensionality. And you might have seen that like in the, I think there was a presentation where I showed you the molecular structure of morphine, for instance, and there's all kinds of wedges and dashes in there. That's what they mean. They're actually telling you that certain things are kind of being held out towards you or behind. And so what we have here, right, is this solid wedge right there is the one that just poked you in the eyeball. And this guy that's behind the plane, right, that's coming kind of more towards me, is going to be this guy. And of course, I could kind of rotate this thing around, and I could draw it in all kinds of different orientations, right? I could draw it like this, where that guy is coming out at you, and there's a dashed wedge coming back here. So don't be confused if you see that in your book or anything else. It's just the chemist is trying to show you the actual three-dimensional picture. So tetrahedral geometries also have, tetrahedral electron pair geometries also have two different molecular geometries. So I'm just going to pick a Lewis structure and build it into what I've already made here. So let's pick on ammonia a little bit. Should erase this too because it's no longer going to be a molecular geometry that is tetrahedral. What we're going to do is we are going to, first of all, draw just a plain Lewis structure for ammonia. And we're going to count up the electron clouds. Remember, we got a lone pair. Be careful. 4 electron clouds is going to be an electron pair geometry of tetrahedral. For the molecular geometry, though, geometry that we have to consider, and you'll notice that we've got that one pair of electrons that are a lone pair. So what happens is that this thing is actually a trigonal pyramidal geometry, right? The one based on 3 actual atoms bonded with one lone pair of electrons. There's still 109.5 degrees right there. And so really what we've done with our original carbon thing that used to look like this is we've removed one of the bonds. So now we just have this little trigonal pyramidal thing. Blah, blah, blah. Okay? And then if we go one step further, and we'll go to water, and then we'll finally be done with this madness. Okay, so let's say that I saw a Lewis structure that was written something like this. First thing I'm going to do, the thing that I always do before I assign geometries so that nobody tricks me, is I count up my charge clouds. I've got 4 charge clouds, therefore I have to have this tetrahedral geometry. Now, I've got to redraw this thing to properly symbolize the molecular geometry. The good news is, though, is that I am essentially going to be just taking this thing and rotating it. I'll show you in just a second. So that I can see that bent geometry, or in other words, that 109.5 degree bond angle. And really what's happening there is we're starting off with our normal tetrahedral geometry, right? But 2 of these are missing. So I'll remove 2. And what I have is this bent molecule. So as I was looking at this Lewis structure, it's not necessarily wrong as a Lewis structure, but it would be wrong if you were told that you had to represent the actual molecular geometry, because what you're doing is you're looking kind of straight at it like that, so it looks like a line, but the second you rotate it, you'll notice that there is actually a bend in that thing. So don't fool yourself. That's a really common trick of chemists, especially in a chapter like this, where you'll draw something like a Lewis structure trying to lead somebody to an incorrect answer. I know, it's sick, isn't it? Yeah, maybe my mom should have hugged me more. Take that, Mom.